Hi, my name is Bill Van Hoos. I'm a civil engineer with Advanced Drainage Systems, actually the manager for structures and materials engineering. I started in corrugated polyethylene pipe in 1998 as an application engineer, worked my way through the ranks from an application engineer to a regional engineer where I covered field services for the field, Michigan, Indiana, and Kentucky, and moved on to the corporate world where it's certainly been involved in new product design, product analysis, dealing directly with customers for that entire period of time on the use of our products. ADS is a world-class leader in the use of thermoplastic materials for pipe production and the use in stormwater and sanitary sewer conveyance applications. Our flagship material is polyethylene. Polyethylene in its most basic form is a series of ethylene monomers joined together where molecular chains are interwoven with one another into a mesh or spaghetti-like structure. PE is commonly used in applications such as milk jugs, detergent bottles, drums, and certainly piping applications as we know it. Polypropylene is similar to PE in its molecular makeup with the addition of a carbon methyl group hanging above and below the central chain. Both materials in this finished form, pipe for us for sure, are typically a homopolymer with additives. Polypropylene is commonly used in applications requiring higher stiffness and higher stress crack resistance than polyethylene. One of the key drivers in stress crack resistance for polypropylene is the carbon-to-carbon bond in the molecular chain. In the simplest explanation, it's harder to strip carbon from carbon than hydrogen from carbon in a polyethylene chain. In polypropylene, there are typically three categories of polypropylene for commercial use. PPH, which is a polypropylene homopolymer, PPR, which is a random polymer, and PPB, which is a block polymer. In a block polymer, the molecular chain has a regular periodic pattern of the carbon methyl group, allowing good crystallinity, which equals high strength. ADS's HP product line uses a block copolymer in our pipe production. With over 20 years of history in sewer and drainage applications, this material is highly crystalline material, offering a good balance of high resistance to stress cracking, high tensile and compressive strength, and good impact resistance. As I stated earlier, it is a copolymer, but it's also further modified with impact modifiers. For an impact modified copolymer, there's a homopolymer in the crystalline region of polypropylene, and there is an ethylene propylene rubber. This is a non-cured soft-set rubber molecule that's set into the amorphous region where the rubber floats literally between the polypropylene crystals. PVC is a true amorphous material where you envision a number of different materials in the recipe being meshed together into the final batter, if you will. As you see in the diagram that's depicted here, there's a homopolymer matrix which allows us to adjust such things as molecular weight or isotacticity or crystallinity for another word. There are also impact copolymer domains which allow us to adjust molecular weight, the EPR amount or this ethylene propylene rubber content, and the ethylene propylene rubber composition or the E to P ratio. While we do consider characteristics such as melt flow rate, izod impact, density, OIT, and crystallization rate, for the purposes of this discussion, the properties that are most of interest to this group are likely the structural characteristics of polypropylene. These values include flexural modulus, tensile strength, and strain limit. Since polypropylene is a viscoelastic material, both short-term and long-term material characteristics need to be considered. As you can see from the slide here, for short-term flexural modulus, ADS uses 175,000 psi. For short-term tensile strength, we use 3,500 psi. And we established a strain limit of 4% for all of our polypropylene products. As you see from this graph, we have tested a number of resins for flexural modulus, and you will see in a few slides we have tested for tensile modulus as well. In verification of the properties used in design, we look at a number of commercially available resins. Forgiving the nomenclature I use on the x-axis of this chart, what we are actually depicting here is the fact that we have tested not only virgin resins, but we have also tested virgin resin with pigment, virgin resin pigmented in pipe production, and actual samples from the pipe wall. You see the 175,000 depicted as the red line there as the short-term flexural modulus. Each of the resins that we show have exceeded that value with the exception of resin I to the far right hand of that chart. The reason I show that is to represent to you that we have an internal process by which we qualify and disqualify resin types. In this particular case, this was a test resin that we had looked at. The value was 160,000 psi for flexural modulus, which would show that we would disqualify that as a resin. When we show performance limits such as hydrostatic limits, minimum and maximum fill height in our drainage handbook, our detailed drawings, any of the information that we provide to you as a customer, we are doing so with the minimum values that we have stated in our product literature as well as in this presentation. We verify that through a quality control procedure that makes sure that the product that we are producing and providing to the field meets or exceeds those lower limits. Those are single point data sets from a single space in time. They are a given resin, they are a given time frame. So as a customer, it's easy for you to come back to us and say, how do you know day in and day out that your material properties are consistently meeting the lower thresholds that you've established? With this particular slide, we show one resin from the previous table over a 5-year production history. And we can state with a 99% statistical confidence that we meet or exceed that 175,000 lower threshold. In this standard Gaussian distribution where the normal distribution is populated around the mean, you can see that the actual mean value for this particular resin is in excess of 189,000 psi. Again, we use 175,000 psi for our lower threshold of flexural modulus. As with flexural modulus, you will see from this table that we are showing the ultimate tensile strength at yield. We have shown 3,500 as our lower threshold for use in design. Of each of the resins that we depicted earlier for flexural modulus, this particular slide shows each of those same resins for tensile strength at yield. We use ASTM D638, which is a standard tensile test used for determining the tensile strength at yield. Our previous slides showed values for flexural modulus and ultimate tensile strength. The last of the short-term material properties that we use for the purpose of design is the strain limit. There are a number of different tests that can be run on strain limit determination. Unlike flexural modulus and ultimate tensile strength, which have specific criteria for pipe design, strain limit is one of those categories that can become very profile specific and material specific. So the test that we run in strain limit determination is a stub compression test. You see from this graph two diameters that were tested, 24-inch and 48-inch. You can see at the table from the right, for the 24-inch sample we have a mean value of 4.77% strain, and for 48-inch we have a value of 4.95% strain. We have established 4% as the maximum allowable strain limit for the purpose of design. You can run into situations where there's question about determination for the ultimate strain limit. There are additional strain limit tests that can be run, such as yield strain, 1% secant strain, and also compression stub testing that we've shown here. The reason ADS opts to use compression stub testing is because it's the only test that incorporates the actual profile geometry in conjunction with the material properties. Polypropylene and polyethylene, the materials that we use for design in our pipe production, are both viscoelastic materials. In viscoelastic materials, you need to take into account short-term and long-term behavior. In long-term behavior, creep is a consideration for these material types. In creep testing, you will typically see 3 stages of creep. There's primary, or stage 1, secondary, or stage 2, and tertiary, or stage 3. Stage 1, known as primary creep, occurs at the beginning of the test, and creep is mostly transient, or not at a steady state. Resistance to creep increases until stage 2 is reached. In stage 2, or secondary creep, the rate of creep becomes roughly steady. This stage is often referred to as steady state creep. In stage 3, or tertiary creep, the creep rate begins to accelerate due to necking or internal voiding, which decreases the effective area of the specimen. If stage 3 is allowed to proceed, fracture will most likely occur. The creep test is usually employed to determine the minimum creep rate in stage 2. For the purpose of design, we have accounted for this creep behavior in all of our fill height tables and performance limits that we have established for you as the customer. From this creep testing, long-term material properties have been established for both flexural modulus and ultimate tensile strength. For long-term modulus, we use a value of 27,000 psi and long-term tensile strength of 1,000 psi. For the purpose of long-term material properties, we use ASTM D6992, which is a standard test method for accelerated tensile creep and creep rupture of geosynthetic materials based on time temperature superposition, also referred to as a SIM test. From testing a resin in accordance with ASTM D6992, one will receive a chart as represented here. By knowing the design stress, in this particular case of 500 psi, the values for long-term creep are established for 50, 75, and 100-year design conditions. Each of those are represented in our drainage handbook. ADS uses a conservative 100-year service life value for the purpose of design. As with short-term material properties, ADS has evaluated a number of resins for long-term conditions as well. In this particular chart, you see a design stress of 500 psi, and the resins that are represented there range from virgin resin pigmented to actual pipe samples, each of which exceed the 27,000 psi long-term flexural modulus. ASTM D6992 allows us to determine the long-term flexural modulus, but it also allows us to evaluate the long-term ultimate tensile strength. As with flexural modulus, ADS uses a conservative 100-year design service life value of 1,000 psi for ultimate tensile strength. Looking at one particular resin, here we see a stress rupture envelope of polypropylene using SIM with a 50-year design service value of 1,172 psi and a 100-year value of 1,119. Again, we feel that we're conservative in using 1,000 psi for the purpose of design. More than 20 years of successful performance history throughout Europe, combined with the intense research and development efforts through ADS all throughout North America, we are confident in the material properties and performance characteristics we have presented here today. These properties, combined with the proven profile designs from ADS, provides the highest level of confidence to engineers, specifying agencies, and owners. Thank you for the opportunity to share this important information with you today.